Okay, so in this video, we are gonna see about Cayley theorem. So, what do we mean by what is the statement of Cayley theorem? So, this comes in group theory, and we're gonna see that. What do we mean by Cayley theorem, and we're gonna prove that as well. Okay, give me a moment. Let me change it. Okay, fine. Yeah. So, yeah, 1 second. Okay. So let me write the statement of the Cayley theorem right now. The statement says any finite group. I'm writing it here. Any finite group is isomorphic to a group of permutations. The finite is very important, and we are gonna prove every finite group is isomorphic to a group of permutations. So it is not like we are taking a group and we are finding all of its permutations. No, it is not like that. We're going to take a group and we're going to form another group of permutations. We're going to prove that these two are isomorphic to each other. So the proof is we're going to first start with the finite group. Let G be a finite group. And then, so here what I'm going to do is I'm going to construct another group from G. But you can also, you don't have to always think of constructing a group of permutations. So you can, if you can prove it is isomorphic to a group of permutations in your own way, then that is fine. But right now what I'm gonna do is I'm gonna construct a group or construct a set of something from G. So for that, let me also let A belong to G. A is an element that is there in G. And I'm going to define a function right now, that is FA. This FA is defined from G to G. There's a new function that I'm defining. FA is defined from G to J. How am I defining it? I'm defining FA of X is equal to AX for every X in G. So this is how I'm defining it. I'm defining FA is equal to FA defined from G to G. I'm defining it by FA of X is equal to AX for every X to G. So this is a new function that we are defining. So whenever we define a new function, we have to make sure the function that we define is a well-defined function. So let me prove that the function is well-defined. So first I'm going to climb the FA that I have defined from G to G, defined by FA of X is equal to AX for every X in G is well-defined. Let me do this. Okay, and after that, we will be proving this. For proving that, let me take two elements from G. Let x, y belong to G. And let me also take such that x is equal to y. So then if a of x is equal to, so from here itself we can tell ax is equal to ay. Therefore, if a of x is equal to f a of y. Therefore, my fa is well defined. So right now I'm going to check the 1-1 condition for round 1 property for FA. So let me check that. So for that, let me also assume let FA of x is equal to FA of y. And that tells me AX is equal to AY. And so according to the cancellation law in groups, whenever we have a group, cancellation law is always valid in group because we have group condition. Cancellation law is always valid in that group. Therefore, according to the left cancellation law, we can tell x is equal to y. Therefore, FA of x is equal to FA of y implies x is equal to y. Therefore, FA is 1-1 function. Okay, so let me go through this one more time. So first we have started with this statement. The statement says any finite group is isomorphic to a group of permutation. So we have taken a finite group. Let G be a finite group. This is a group, and I'm taking an element from G, and I'm defining a function FA based on the element that I have taken. That is FA, where A is from G, and FA is defined from G to J, defined by FA of x is equal to AX for every x in G. And after that, what I'm doing is I'm proving the whatever I have defined here, I'm proving that is a well-defined function as well as that is an 1-1 function. Okay, let me talk about the onto also. Let me check the onto. So now this function, if you see it carefully, this function takes G and maps to G itself, right? It takes G elements from G and it takes maps to G itself, and G is finite. So any one function defined on a finite set it should be onto. So FBA will obviously become onto. You don't have to actually prove. If we can prove, we can also prove that nothing is wrong. But you don't have to actually prove. This is obvious. Therefore, what do we have right now? We have a bijection. FA right now is a bijection. So we have a bijection from a set to itself. The set is also finite. So we have a bijection from a finite group to itself, a finite set to itself. Then the function FA we can call using a special name. We can call FA as a permutation right now. So whatever we have defined that is a permutation right now. So FA has become a permutation because it is a bijection from a finite set to itself. So FA is a permutation. Permutation on where? It is a permutation on G. And then what I'm gonna do is this is from G I have constructed a permutation. So what I'm gonna do is I'm gonna define or I'm gonna collect something else and I'm gonna put that in G dash. That is G dash is a set of all or collection of all FAs, collection of all permutations for every A in G, right? So for every element A in G I can define FA. So I'm gonna basically collect all the permutations that I can define using an elements of G. So G dash is FA where A belongs to G. So this is the step 1. In step 1, what did we do is we basically constructed a set of permutations. That is what we have done in G dash. And then if you look at it carefully, the cardinality of G dash, if no two functions are equal, then the cardinality of G dash will be equal to n, the cardinality of G. That is cardinality of G dash is equal to cardinality of G if no two elements in FA are equivalent, because it depends on A. So the number for 1A will be having FA, therefore for cardinality of G elements will be having that much of function permutations here. So right now what we are going to prove is we are going to prove the group that the set that we have constructed actually forms a group under the composition of functions or product of permutation. So we are gonna prove that set that we are gonna formed that we already formed is a group under composition of functions. One second, let me write it. Yeah, so G dash we formed, right? This is step 2. G dash we formed, and we're gonna what is G dash? G dash is a selection of all permutations that can be obtained from G. And we are going to prove this G dash is a group under composition of functions. And we know for sure composition of function is always associative. Therefore, it is always associative. Therefore, we have to check for closure, identity and inverse. For closure, let me take two elements from G dash. Let FA and FB belong to G dash. So, I have to prove FA composition FB that is also in G dash. So for that, let me consider FA composition FB of x. And this is FA of FB of x. And this is FA of BX. And that is equal to ABX. And remember all the elements A, B, X, everything is there in G. Everything is there in G and G is a group. And therefore G is a group, it is associative, right? All the G has to be associative because it is basically a group. So this is equal to ABX. So you can also prove FB composition FA is also I'm sorry, that is BAX, but right now we don't need that. Why do we need that? Okay, so we actually have FA composition FB of x is equal to ABX. So which means FA composition FB can be written like this. This is true for every x in G. This is true for every x in G. Therefore, what do we have? We have this function FA composition FB is equal to FAB. Both are same, right? Both are same. And look at AB. A is an element of G, B is an element of G, therefore AB is an element of G. Therefore FAB will be there in G dashed, because for every element in G will be having corresponding F permutation that we have collected in G dash. Therefore, this FA composition FB is equal to FAB, and AB is an element of G. Therefore, basically FAB should be there in G dash. Therefore, the closure property is true. Now, right now, we'll try to prove identity and inverse. Okay, so for identity, what I'm gonna do is I'm gonna consider something like this. This E is an element of G. Let me take E is an element of G. So F E of X is basically EX for every X in G. So let me talk about what about FA composition FE of X. So FE composition FE of X is equal to FA FE of X. So that is equal to FA of EX. That is FA of X. That is equal to AX, right? What is AA? AA is basically FA of X. You would have stopped here itself. Okay, fine. Therefore, what do we have? FA composition FV is equal to FA. You would have stopped here itself because we are getting the same thing again. So, similarly, we can prove FE composition FA is equal to FA again. Therefore, FE belong to G dash will be the identity. And then let me talk about the inverse of it. Inverse also you don't have any problem, because basically the set of permutation is inspired from G. When G is a group, so everything falls in place. So let me consider FA. FA is there in G dash. For this FA, I have to basically find the inverse, right? So if FA is there in G dash, what about A? A will be there in G. And basically G is a group. Therefore, A inverse is also there. A inverse will belong to G, because G is a group. For A inverse X is for G. And for whenever we have an element in G, we can talk about the permutation FA inverse. And how did we define FA inverse of X? This is A inverse X. Have this. So right now I'm going to consider FA composition FA inverse of X. So this is equal to FA of FA inverse of X. That is equal to FA of A inverse X. That is A inverse X. That is A inverse X, because it is associative. This is EX, that is X, right? Or FEX. FEX. Okay, so basically what we have is FA composition FA inverse is equal to FE. You can also prove FE is equal to FA inverse composition FA. Therefore, FA inverse belong to G dash is the inverse of FA. This is the inverse of FA. So basically, we proved the existence of inverse also. So we proved closure, associativity is always there, and we proved identity, and we proved the inverse of it. So all this property comes into place very easily because of the fact that G is a group, and the set G dash basically is inspired from G. That is why everything falls into place correctly. So right now, what do we have? We have a group of permutations. Initially we had a set that we have constructed from G, and right now we have a group. Since we have proved that is a group. Right now we have a group of permutations. So meanwhile, I would also like to tell. So whenever you have FA composition FB or something, since we have already proved FA composition FB is equal to FAB in closure, you can also make use of it. You can write FA composition FA inverse of X is equal to FA inverse of X. You can also write that. Whatever is comfortable to you, you can always do that, as long as it is logical. So, okay, fine. Having said that, now that is step 2 is finished. At the end of step 1, we had a set of permutation. At the end of step 2, we had a group of permutations. So now what we are gonna do is we are gonna finish this theorem of that is we are gonna prove the G is isomorphic to G dash. G is basically a finite group. G dash is a set of group of permutations that we have constructed from G. So in order to prove something is isomorphic to each other, I'm going to define a function. Since we have already had f and those kind of stuff, let it be phi. I'm going to define a function from G to G dash. And all the elements of G will be elements, and all the members of G will be kind of an elements. All the members of G dash are functions or permutations. So remember that. So how am I going to define? I'm going to define, if you're going to take an element from G, phi of A, I'm going to map it to FA. That is, for A, I'm going to map it to FA. For B, I'm going to map it to FB. So like that, I'm defining a function. One second. Let me erase this. Yeah. And this I'm defining for every element in G. So since this is a new function that we have defined, we have to make sure it is a well-defined function. So climb phi is well-defined. Okay. So yeah. So what are we going to do is, we're going to make sure this phi that we have defined is well-defined. So let me let me take two elements, let A, B in G, such that A is equal to B. So if A is equal to B, then basically that means that AX is equal to BX for every X in G, no matter what the X is. And what is AX? AX is FA of X. And what is BX? FB of X. This is true for every X in G. Basically, the function value is same for every X. Therefore, the function itself has to be same. That is, FA is equal to FB. And FA is nothing but phi of A. FB is equal to phi of B. So whenever we have A is equal to B, we are getting a phi of A is equal to phi of B. Therefore, phi is definitely well defined. Yeah. So for the function, we don't have to worry about it. Is a well defined function. So right now, I'm gonna prove the function f phi is isomorphic. So in order to prove function f is phi is isomorphic, I'm gonna prove it is 1 1, it is on 2, and then it satisfies the condition of homomorphism. First, let me start with 1 1. I'm gonna right now prove phi is 1 1. For that, let me take again, let A B belong to G, such that I'm gonna take phi of A is equal to phi of B. So how did we define phi of phi A? FA is equal to FB. The permutation is same. If the permutation is same, the values at every point is also same. That is, FA of x is equal to FB of x for every x in G. And what is A? This is AX, this is BX, right? For every x in G. And G is a group. And basically, cancellation laws are valid in group. According to right cancellation law, if you cancel it, you have A is equal to B. Therefore, whenever you have phi A, if A is equal to phi of B, you are getting A is equal to B. Therefore, phi is 1 1. And then we're gonna prove phi is onto, and phi the onto condition will obviously fall. Anyhow, we'll try to prove this. Okay. So let me try to prove phi is onto. So for onto, I'm gonna take phi is basically from G to G dash, right? So I'm gonna take an element in G dash. Let FA belong to G dash. So according to the construction itself, FA belong to G dash implies A is there in G. That is the idea, right? A is there. FA is there in G dash. According to the very construction itself, A is there in G. If we consider phi of A is equal to FA. So which means that for every FA in G dash, there exists A in G such that phi of A is equal to FA. Therefore, phi is onto. Every element has a pre-image. Okay, so basically phi is a bijection right now. Phi that we have defined from G to G dash has become a bijection right now. It is a bijection. Okay, so let me try to prove this homomorphism condition. One second. Let me try to prove the homomorphism condition. Okay. So let me take again, let A and B in G. Let me talk about phi of A plus B. Or A plus, in G, we let me have this operation to be a product right now. And depending upon the operation, you can always change, right? So whatever the operation of G, you can put that operation here in this place. And in G dash, it is composition. You don't have to, because we have proved G dash is the group under composition only. So phi AB. Phi AB, according to the definition, it is FAB. Okay. So have this. And then we are gonna prove find phi A dot phi B. So this is FA composition FB. So here it is composition, because Phi of A is a permutation, phi of B is a permutation, this is FA composition FB. And while proving closure property, we actually proved FA composition FB is equal to FAB. So basically phi of AB is equal to phi of A composition phi of B. So we proved the homomorphism condition also. Altogether phi is an isomorphism. Phi is an isomorphism. And that means that G is isomorphic to G dash. What is G? G is a finite group. What is G dash? G dash is a group of permutation. Therefore, any finite group is isomorphic to a group of permutation. That's all. If you have any doubt, you can leave that in comment section. Thank you.